Amy because we're using the DES Teams account, and I think she's got a presentation for us. But in any case, I'm Kirk Maloney, president of the Lake Kanasatka Watershed Association. Up next,
Kevin Kelly, LKWA Water Quality Chair.
Scott Apgar, Secretary, LKWA.
Eileen Evening, Treasurer.
Chris Wallace, Communications.
That Mike.
Yeah, you got a little echo going on there, Eileen.
Yep. Figure out.
I'm Larry Pizer. I'm the new guy on the board.
new guy on the block.
Yeah.
Any more LKWA people?
This is Jana. I don't know if you can see me. I'm not seeing myself up there. And I've been on the lake. I don't know. I'm Mr. is having problems logging in. Been on the lake 40 years and been on the board for 2.5.
Scott Parker.
Scott may still be having audio issues. We still can't hear you, Scott.
He's wearing the flannel shirt and has glasses, for those of you who don't know him. And he's waving. How about UNH team?
I'm Bob Craycraft, UNH Lakeside Monitoring Program.
Amanda McQuaid, also with UNH.
And I see Bree Rossiter has joined us.
Hi, everybody. Bree Rossiter, Conservation Program Manager for LWA, and Maya is on as well. So go ahead and introduce yourself, Maya.
Hi, I'm Maya, and I also work with LWA.
Welcome to the team.
Thank you.
Kirk, I can jump in. I'm Laura Deemer. I work for FB Environmental Associates.
Great.
And we have several from DES. I'll start. Amy Smagula, Chief Aquatic Biologist from Department of Environmental Services.
And I'm Dave Nails, I'm the Administrator of the Watershed Management Bureau here at DES. Michelle?
Michelle Boozy, I was the temporary Cyanobacteria program coordinator this past summer.
And I'm
You were a busy girl.
I'm Georgia. I'm the Exotic Species Program Coordinator at DES, and I was previously at UNH for a long time.
Oh, there's Jana. She made it. Great. Did we get everybody? I think so. All right. I'll turn the meeting over to Amy. And Amy, you take as much time as you need. We'll see how we can, learn something from what we're seeing this fall and try to piece some puzzle pieces together, I guess. I don't know.
Mm-hmm. Sure thing. Thank you. And I'm going to be joined by Laura Deemer and Amanda McQuaid as well. When we were looking through the information from the Lake Association and the board with all the questions that you guys had, we thought it would be a good idea to put together a presentation that went over where we have been and where we are now for Lake Kanasatka. And we did try to weave in all 22 plus questions that you guys posed to us by email, which was really helpful for context. So we have about 15 to 20 minutes of presentation. Laura's going to start, followed by Amanda, and I'm going to wrap it up as we go through. So I'll turn it over to Laura to start. Certainly, if there are questions at the end that we didn't answer, we're happy to discuss those through the balance of the meeting and then see what else you guys may have to ask us. So Laura?
Yeah, thanks, Amy. So I'm not sure who to give the photo credit to, but really lovely photo, rainbow over Lake K. So you'll see this slide at the end as well, but we just thought it'd be a good idea to just give you the very high level main points. and how, we're laying out these points throughout the presentation. And then, sorry if there's feedback. So I'm going to be starting off, and I'll pass it to Amanda, and then Amy will bring us home. So one of the first points that we wanted to highlight was that, the alum treatment did its job. The alum treatment was meant to reduce the internal phosphorus loading that was occurring in Lake Kanasatka in late summer into the fall each year. That was driving some of the more severe cyanobacteria blooms, especially when we saw in fall of 2023. The alum treatment wasn't meant to treat the cyanobacteria directly. It was just cutting off a major nutrient source, a major food source for them. I also, in a few slides, want to just go over the difference between, these major whole lake blooms versus shoreline accumulations, and just trying to highlight that scale and magnitude do matter when we're talking about these different types of blooms and how they can form and present themselves in the lake. I do want to emphasize that the external phosphorus load continues to be the major driver of nutrients into Lake Kanasatka. The alum treatment reduced that internal load by 80 to 90%, but it was only representing about 20 to 25% of that total load. So it was an important source. It was a significant source, but we also want to emphasize that the external load was the majority driver and continues to be today. And then also emphasizing that restoration is a process. Lake Kanasatka does need more time to find its new balance. It's been out of sync for a number of years now in a cyanobacteria dominated system, and it's going to take time for the food web to reestablish, and Amanda's going to be diving into that a little bit more. Okay, so just reviewing the results of the alum treatment. And like I said, it did substantially reduce the internal phosphorus load. The figure that you're seeing right now is looking at phosphorus concentrations in Lake Kanasatka over the course of a year. You can see this is Julian calendar days here. The orange lines and points that you see are pre-alum treatment. So you can see in 2022, a steady increase in phosphorus concentration over the course of the summer season, and then even more so in 2023, which ended up with the most severe bloom that we saw, like I mentioned, and obviously we're all aware of. But then post-alum treatment in these blue lines, so the deeper blue is 2024, the first summer season after treatment, and then the 2025 data that we have so far. And you can see that it really flatlined that average phosphorus concentration throughout the season, which was really great to see. This is another way to look at the data. This, thank you to Georgia for pulling this figure together. This is phosphorus concentration, but instead of looking at the average water column concentration, we're just looking at the very deepest 13 meters at the deep spot and what the maximum concentration was in any given year. So you can see that, fairly high counts in 2021, 2022, and 2023. And then post-alum treatment, those bottom readings have reduced pretty dramatically, which is great to see. There were some questions that you all posed as far as treatment coverage, and I just wanted to point that out quickly that the alum treatment that was done by Solitude, they have some pretty advanced GPS tracking software and technology on the barge, and they also have flow meters along the hoses as the chemicals are being discharged into the lake. So these, it's very similar technology to like large scale farming. Combines or fertilizer spreaders, herbicide spreaders that they have, where they can really track exactly the path that they're applying the aluminum compounds throughout the lake, and then tracking how much is actually being delivered at any given point. And then that's all summarized in their final report and given to us at the end of the project. And so there was complete coverage of our target area, with the dose that we were targeting. There were also some questions on longevity of the alum treatment, and we obviously, there's always some unpredictability with these things. There were some models that we used to try to estimate that. But I did want to, there were some, I think, questions on how much cyanobacteria post-alum treatment was maybe settling on top of the flock that's there, and how much that might be reducing the efficacy or longevity of the treatment. And of course, that's going to have some effect, but I do still want to emphasize those external inputs settling on the lake, and some of that is, cyanobacteria taking up that phosphorus within the water column, and potentially settling out or remineralizing that phosphorus. There's a lot of different cycling that goes on within water bodies, but a relatively small fraction of that is settling as cyanocels when you're considering the entire amount of material that's settling on the lake bottom in any given year. And that does happen relatively gradually, right? We usually measure that in millimeters per year. And the flock that's down there in the sediment still has some binding capacity left. So, the more that it's interacting with new sources of phosphorus, as it mixes deeper into the sediment, it's, potentially binding that phosphorus, and will continue to do so. Usually for a few years it can be active, but it does age over time and will become less effective every year. So, we did want to kind of just remind you of where we came from to kind of put these blooms into perspective, right? We're all familiar with this photo. This is kind of what really elevated Lake Kanasatka, not just from a local issue, but to a regional concern, since this bloom did migrate down into Blackie Cove. But, this was the fall 2023 bloom. It was whole lake. You've got your pea soup green water that we're looking at. And then just trying to put that into perspective of kind of where we are now. And, we're still seeing some cyanobacteria, but this summer it's been largely presenting as shoreline accumulations. That is important to track, and we're so glad that we do have that information. And I think it's just important to understand how these are forming, right, and how to treat them as far as monitoring, management, and kind of public messaging with advisories with the state, which we'll get into more. So with the context of blooms, obviously cyanobacteria, are a natural part of our ecosystems. They're the reason that we have oxygen in our atmosphere, and why we're here today. So it's never the intent, nor is it possible to completely eliminate them from the system. What we are trying to do is we're trying to control and limit their overall dominance in a system, right? We're trying to achieve a balanced composition that includes various phytoplankton, including cyanobacteria, right? So we're trying to make sure that these cyanobacteria do not get out of control into these, bloom conditions, but we have a good balance of diatoms and greens and golden browns in a healthy ecosystem. So the difference between, whole lake blooms and shoreline accumulations, I just wanted to touch on. So, again, I've got this pre-treatment photo here, and just emphasizing that scale and magnitude really matter, and for a number of reasons, right? We're thinking about the distribution of cyanobacteria, how dense that cyanobacteria is in any given location, how long it's lasting at that distribution or density, anywhere in the lake, and then how persistent those blooms are as far as recurring or, coming back year after year or at specific times of year. So in this case, the pretreatment bloom that you see here, right, it was just completely dominated by cyanobacteria, and throughout the water column and throughout the lake. That contrasts with, then when we see these shoreline accumulations, it's often that we have these low density concentrations of cyanobacteria in the water column, and those can rise to the water surface and then more easily be blown to our shorelines from wind and wave action, so that what was a low density concentration in the water column that wouldn't make for an advisory, in these conditions, when it's concentrating along these shorelines, it's obviously at levels that can trigger advisories. But then you're talking about, small areas along the lake, whether it's ribbons or kind of clouds that form along these shorelines. So, and then, just making a note here too about the sampling method also matters as well. Even just looking at this photo here and how you would collect a sample to be, representative of the system, and also ultimately the risk level that bloom presence or cyanobacteria, growth presence like this would mandate. So I'm going to pass it off to Amanda, who's just going to talk a little bit more about cyanobacteria dynamics.
Thank you, Laura. So understanding cyanodynamics, we could go in a lot of different directions, but we wanted to focus a little bit on Dolichospermum, which actually is the most dominant type of cyanobacteria we see in New Hampshire lakes, especially in June. So somebody asked, and I think a lot of people are wondering, if we got rid of the phosphorus, then how are cyanobacteria getting their phosphorus? Really, the answer is everywhere, and I know that's not like a very direct answer, but it's true. Phosphorus is everywhere. It runs off in different capacities, but it's also in the lake itself. So when we talk about this type, Dolichospermum, there's different things to consider and different times of year to consider how they might be behaving or how we might see them. And so, you guys kind of had two events. I think we'll get to those details later this year, but there was maybe an accumulation in June. Maybe Michelle could also just correct me if I'm wrong, where we had probably more of like that spring form that you see up here. I don't know if you can see my cursor. This colony here of Dolichospermum is what we typically see in New Hampshire lakes, and sometimes they can have toxins and sometimes they don't. And that is something that we're also trying to grapple with. But all of these cyanobacteria are very different, in fact. So when we're talking about them, we're not just talking about one thing. It's really is talking about, how different plants need different requirements. So they do have a lot of great ways of getting around it. And so nutrient requirements, habitat distribution, and even the food web really drive this relationship. So Without getting too technical, there are a lot of variables here, and it's not just phosphorus to be concerned about. But we often see that we can control in studies. We've seen that we've read, and there's a lot in the literature about treatment like this, where you can treat the nutrient source, but sometimes it takes a little time for the food web to catch up. So we'll talk a little bit more about that. But before getting all into that, I think one of the big findings that was interesting from just simply monitoring with lake slate monitoring this summer, spring into fall, in fact, was that it was clear that after the June rain, which we didn't have a lot of rain, that we had an increase in surface phosphorus. And there could be a lot of reasons for that, but what was evident was what, FB and Laura have already explained, is that it's a lot of external nutrients still getting in. Of course, that's always going to be the problem for every lake. However, there are some interesting food web dynamics, and there's also some interesting nutrient dynamics. So without putting this into like a lecture mode, just to kind of describe this image here, in fact, we are still seeing phosphorus that's 9 parts per billion up in the surface water. And we have a lot of studies and backup to show that there's like this rule of 10 when surface water is approaching 10 parts per billion, that cyanobacteria tend to kind of take off and do better. I'm not saying that is definitely the case here. It's just another thing to kind of pull from the literature to consider, because we're learning a lot here as we monitor and study the lake. There was also a question about road salting and if that would have affected maybe nutrient inputs. More so, does salt cause cyanobacteria? Not necessarily, although any sort of disturbance in the water can kind of cause like a different cascading trophic interaction, basically, where one thing affects another and there's a trickle effect on the food web. So we do see years that obviously weather is very much a factor and water levels are another factor. And so I love this diagram I believe Laura put together to show that phosphorus is really everywhere, and they have different strategies for surviving. And so it is very likely that every time you see a shoreline accumulation, all of these growth cells are just kind of sitting in the sediment. And then you have one rain event in June, and that might uptick and like kind of push them back out. And then they kind of get a surge of nutrients and take off as spring comes about. Next slide, please. So I don't want to get too nitty gritty in all the data, and this is something that Bob and I and our students are putting together. However, I know the question is, what were the data? How did they look? And we even added another site on October 23rd, which I was not there for. So Bob and Georgia can speak to that. But basically, I wanted to kind of put that rule of 10 in context here in this graph. That, all of the surface water phosphorus that we collected at the deep site was below 10. It increased to 9 when there was rain in June, and then it increased to 9 after lake turnover, which is where, I guess in the next graph, if you could go to the next graph, after this. In fact, fall turnover is really what we started to see in the deep water. So before I get to the next graph, sorry, we did get photos and a lot of good evidence and just kind of record keeping from Kevin and some others on how the water was looking. And so this photo here represents sort of, again, that like lake-wide kind of greenish hue. But Georgia was able to look at the sample from October 23rd. Her, Bob, and Lisa were actually on the lake and did a little bit extra that day. And you can see from that plankton haul, that top photo with that cup, it was very dark green. But after Georgia did a count, it was determined that only about 5% of what we're seeing in that cup is cyanobacteria. There was actually a lot of Chrysosphaerella, which is a golden brown algae that can bloom. And in fact, we saw predominant in almost all of our samples this summer, at least on the Lake Slate monitoring program side of things. So for some reason, Chrysosphaerella did excellent this year across lakes. and they can also be a bloomer like this. However, they did determine from a sample from Kevin, I believe, from this sample, from this photo, that there was still Dolichospermum, and it actually was a different species than the one I showed you previously. So the lake is still showing that it has a little bit of Cyanobacteria diversity, but it is not necessarily dominant. And so fall turnover matters. And so if you could go to the next page, please. I just wanted to also show, and again, the total phosphorus data was all put together, or results were analyzed and put together by Bob and Georgia. And in this year, we have a month-to-month kind of look at the hypolimnion, which was really just a 0.5 meter to 1 meter off the bottom. It's just that first kind of layer that we can look at to see, is there an excess of phosphorus kind of sitting there or coming out of the sediment? And again, I have the 10 threshold there just for context, but you can see that like on the onset of stratification, and there's a little bit of anoxia at play, that phosphorus does increase to about 20 in August, which we find to be a pretty telling time during stratification. But there's also a huge population of, well, I wouldn't say huge, I'm sorry, I'm thinking of Wakanda because I met with them earlier. There is a tiny population of Planktothrix down at the bottom of the lake, and those types really like to live deep. In contrast, Wakanda does also have this at much greater scale. But what is great to see about this is that this is the breakdown of the graphs that Laura already showed you, but just more in context to time period, and that Georgia put together. So this would be that average of 14 in the bottom, which is holding as far as the treatment goes, as far as that hypolimnetic phosphorus goes. So to compare, before aluminum, it was 200 to 300, and now it's 20. And that's more, it's kind of in line with a lot of other lakes so far that we're monitoring, but we have yet to monitor enough lakes to really determine how many lakes are exceeding this level. So I think that this kind of increase is in part due to the Planktothrix, that cyanobacteria abundance as well. You guys also had questions though about a potential other deep site, and that we named here near Sandy Cove. So on October 23rd, Bob and Georgia and Lisa did get all the parameters we would normally get, but just for reference, the lake had already turned over, meaning that it's already pretty well mixed again. And so you can see at the depth we could get at that site, that around 9 parts per billion of phosphorus was found on October 23rd, but we can't say too much about anoxia. So if it's something that the board and the group wanted to continue monitoring, you'd have to just let us know how, we'd get to a follow-up meeting on a sampling plan in the future. But this will all come out in the Lake Slay monitoring highlight reports. And we also now still also want you to explore our data visualization platform that we have on the Lake Slay monitoring website. So you can look at data so far, compare results to other lakes so far, and then we will have an updated report as soon as possible, but it takes us some time. I think I might have one more slide, and it's just to also point out that I have several students that are very interested in plankton, and so as a result of actually meeting with New Hampshire DES, we had a big lakes meeting, in part to kind of get ahead of the spiny water flea, but also just to get more lakes to be able to look at plankton, which is just another variable that is easy to ignore in this scenario. We can control bottom-up nutrients, but there's also a food web dynamic that controls what's available. So we do think more monitoring will give us the time to find a new balance, but I just wanted to point out what the Daphnia, what a water flea is. Daphnia, also known as water flea, are basically like the grazers of the lakes. They are considered great to see in lakes in general, but there's so many different species. And what's interesting is that Kanasatka has this one. This is Daphnia ambigua. It's one of the smallest of the Daphnia. And so while you can see that green gut, that's probably a good dose of cyano and golden brown algae, they're not usually as efficient as other Daphnia at really filter feeding. So that's part of the research that I'm doing with students at UNH. We're asking how do grazers and food web dynamics influence the growth and distribution. And that's really dependent on the type of cyanobacteria, but also the type of Daphnia. So we feel really great about the level of phosphorus. It seems to be back in balance. It looks very much in line with other New Hampshire lakes. But we have been kind of neglecting the plankton. And so we're hoping that a little more clarity will come out of that, but time will tell. We do have a student right now who's involved in an independent study and will present it. We have this undergrad research conference. So I'm hoping after this, we could even have a follow-up meeting with both Wakanda and Kanasatka to share some of the ongoing results that Georgia started. So I think that I am through with this portion of the questioning or presenting, and I'll hand it over to Amy. Thank you.
All right, thank you, Amanda. So I have a few slides to go through just to talk about more of where we were and where we are now. So the first one that I'm going to talk about is the history of the bloom days on Lake Kanasatka, starting back in 2020 and moving to present day. When we first started this, starting observing the blooms in Lake Kanasatka, it was around 2020. Prior to that, we don't have any record of blooms in our database, at least. But in 2020, there were 24 days of blooms, mostly late summer, and some of those were mixed between lake-wide observances and shoreline observances. This is around the time when Amanda was running the Cyanobacteria program in 2020, 2021. And then we had a shift over to Kate Hastings after that. And now Michelle was running the program in 2025. So we did have a shift in people that were running it, and our methods were a little bit different. And I'll talk about a change in methods between 2024 and 2025 before I get into 2025. But anyways, we started off with just a few days of blooms, or more than a few days. 2021, we had 22 days. Again, late season with a mix of lake-wide and shoreline ribbons. Moving into 2022, we had a lot more days, 92 days total. Most of those were shoreline
Amy,
ribbons.
can I interrupt for just a second? This is Scott. We know a lot of this historical data. I'm getting concerned we won't have time to run through Q&A. Is it possible we can speed through this and get to more of the nuts and bolts of the questions?
Yep, and we're trying to answer those questions as we go through, but I will zip through this a little bit more quickly. Thank you.
Thank you. Thank you very much.
Yeah, so we have seen a fluctuation of number of days of blooms. Last year, 2024 looked really good with the alum treatment where there were many fewer days. And then 2025, we started to see a lot more. And I guess the context of my going through this here is that now we're starting to see much more shoreline blooms and ribbons of blooms, as opposed to some of those really big blooms that we were seeing before. And I think that some of the information that is coming out may be in context of how some of these blooms are being sampled. So next slide. Okay, thank you. So what we can expect with an aluminum treatment is that it will still allow cyanobacteria blooms to break through that treatment. Next bullet. The aluminum is added to the water not to be a control of cyanobacteria, but to control the nutrient release. When it's put in the water, it strips nutrients from the water column during the treatment, and then after that, the aluminum settles to the bottom and it binds that phosphorus released from the sediment, but it's not an algicide. It's not going to kill or control the algae for the long term. And those cyanobacteria can take up nutrients everywhere. Even though we've limited the nutrient release from the lake sediments, they can still take nutrients up from that 20 micrograms per liter that you were seeing that Amanda reported. But they can also take it out of the water column, near shore, far shore, so they can luxury uptake that and then reserve those nutrients for a later time. Another thing that we think is happening is that those tremendous blooms that we saw for a few years were dropping resting spores in the bottom of the lake. Those are called aconites. And those can be viable for several years, even up to 100 years. So you may have a bunch of resting cells for cyanobacteria that are down in the lake sediment and are driving some of those blooms now. And there is precedent for this. We did see some lakes, like Nippo Lake in Barrington, that was treated in 2021. A lot of similar circumstances to what we saw in Lake Kanasatka with anoxia and internal load and degree and magnitude of cyanobacteria blooms. Though that lake did bloom, not bloom, but it did have some cyanobacteria ribboning along shore 2 years post-treatment. So it's not unusual to have that continue to happen from a combination of aconites and enough nutrients still in the water column to support those blooms. Next slide. I do want to point out that there have not been a lot of toxins associated with the blooms that occurred in Lake Kanasatka. I know the blooms are unsightly, but from a public health standpoint, we think of blooms in terms of toxin production. And this graph here shows you sample days when blooms were reported and samples were collected that we saved for analysis. And on the upright, on the y-axis on the left is concentration. So the two arrows over on the right, the green arrow is the threshold for recreation for Cylindrospermopsin, which is one toxin. The blue arrow is for microcystin, which is another toxin. Anatoxin, the orange bar, does not have a threshold for recreation, so we don't have an indicator for that. But I can tell you that the microcystin was only above recreational threshold on 3 occurrences, twice in 2020, once in 2022, and then all of the other times it was either absent from the samples or very low concentration, well below 5 micrograms per liter. So that is good news in that most of the time that you've had blooms, they have not been toxic. Next slide. Some of the things that we'd like to take a look at in the future, possibly just to learn some more information, like we said, continued monitoring is beneficial. We want to do some through the ice sampling, possibly this winter, to check the algal population composition. So use a plankton net to pull a haul up and just look at what the composition of the plankton is. The sample over on the left is from Partridge Lake, which was treated this year. And it's an example of a bloom that was happening under about 2 feet of ice this winter. So blooms can still happen under the ice. So a dynamic of what's going on would be helpful. We'd also like to check the phosphorus concentrations in the lake just to see what they're doing under ice. Sometimes you can have internal load under the ice. We'd also like to take a look at the sediments to see what the count of is for the aconites, or those resting spores of the cyanobacteria, to know if there is a big bank of those in the sediments that could be driving blooms. And we do also encourage everyone around the lake to be observant for blooms throughout the growing season. If they're washing up on other shores, if there are ribbons or scums that may be hard to see, or when you're boating on the lake, making observations about blooms that are out there. Everyone should have their eyes on the water, looking and reporting things. Next slide. So some recommendations for next steps. We do want to remind you that there are a lot of steps that can be taken to restore a lake, but there is no going back to the original pristine condition, whatever that might be defined as. So continuing to monitor water quality and cyanobacteria occurrences is really important. It will tell us if and when internal load starts to come back. And we do want to continue to stress external sources. Now that internal load has been accounted for with the aluminum treatment, 95% of the remaining load is attributable to watershed land use. So it's very important to continue the watershed work. And as both Laura and Amanda stated repeatedly, we need to let Lake K come back into balance. The lake has seen a dramatic swing over the last 4 years. 3 years of worsening bloom condition and rising internal load, aconites building up, and then the aluminum treatment was applied, which does drastically change the aquatic food web, and allowing that to recover over a couple of years so that those zooplankton can graze back some of those algae would be helpful. And that just doesn't happen quickly. And I know that it's super easy to go online and explore, how do I manage my lake? What can I put in my lake to make it better? Aluminum, phoslock, drawdown, bottom raking. These are all things that were brought up to us, and it's way too early to be considering any of these. You just had a massive in-lake management practice that happened last year, and the lake is not ready for another management practice. We need to see how this plays out and let things equilibrate some before we consider other factors. And not all those factors that you find online are going to be the solution for lake management. So next slide. So we just want to revisit what Laura started with at the very beginning, in that aluminum did its job and the scale and magnitude matter when you're collecting blooms. One of the things that I was trying to point out with the annual collections of samples is different people are collecting different samples over time, and how you concentrate samples when you collect them matters. If you're picking away and getting all the scum material that you can off the surface, you could be overly concentrating those samples and skewing the results. So we just need to have a consistency with sampling just to make sure that we're seeing consistent method from time to time. Keep working on that external load, and restoration is a process. It takes a long time. It took a long time for Lake K to build up to the point where you started having massive blooms, and it's going to take a long time for it to restore itself with all the efforts that are going into it. So with that, I think that was our last slide, and I believe that we are happy to answer questions at this point.
Wow. I'll say wow, because that's a lot of great information. And yeah, I really appreciate the effort that you guys all put in and the collaboration between Amy and Amanda and Laura on that presentation. It was very, very, very well done. Thank you. Right now, I don't have a single question, but there may be somebody in the board that might. So floor is open, folks.
So I guess this is Scott. I'll throw one out there. I still don't have a good feel as to whether it would be effective for us to treat, effective and or necessary for us to treat the shallow areas that were not part of the initial target area, but seem to be showing up the majority of our blooms at this point. Could someone address that one for me? It's a tough one, I know, but that's the big one on my list at this point.
So I can start. I'm sure Laura's going to want to jump in on this one. So nearshore treatments are not common. When you're using aluminum, it's because it is a zone where the phosphorus is not binding with anything else, because it's anoxic. And when it's anoxic, the phosphorus comes off iron and manganese and all kinds of other products. The aluminum works in conditions where there's no oxygen to bind that phosphorus. In the nearshore zone, most of the time, you would have plenty of oxygen in that zone. So it's unlikely that you're going to get the best bang for the buck with aluminum in that zone. There are other things that are happening there with recycling of nutrients as plants decay, as algae grows, that may not be captured by that aluminum treatment in that zone. And I know Laura has some concerns about mixing of bottom. Laura, do you want to chime in? Sensitive areas?
Yeah, I think, Scott, one of the points we were hoping to make through this presentation is that the cyanobacteria are getting their phosphorus everywhere. It's not just, shallow, untreated areas that they're extracting this phosphorus from. It's everywhere in the lake. I did go out there one day this summer, and then I heard obviously from Amanda and Bob and others who were out there as well that, there were cyano densities, Dolichospermum, and a little Planktothrix, even the deep areas of the water, right? They're able to extract the phosphorus they need anywhere. From a management perspective with alum, the shallow areas are really more ecologically sensitive than our deeper areas, and we want to really protect those areas and avoid a full lake treatment that's that is not typically done for most lakes for that reason alone.
Is there anything ecologically acceptable in these shallow areas, or because what I'm kind of hearing is we have to put up with this. There isn't a fix in these shallow areas, and until the lake reaches an equilibrium, which that was another one of my questions. I'd like to understand a little bit more about what that balance is. But until we, a couple of years down the road, hit that equilibrium, we are stuck with blooms as we have them today. And for me, that is just terribly disappointing. You know,
I am not a lake manager, but I just want to say that there's something of an upwelling current. Upwelling is just when there's sort of a dynamic of when water comes into the lake, what temperature it is and what time of year it is, where you are going to see some of those bottom nutrients come up. So even up to 20 parts per billion, it's enough. There's a lot of lakes that have that level that still experience cyanobacteria. But what you're seeing on the shore is really just an accumulation, and not necessarily the source. And so unfortunately, like even where Kevin lives, we saw sort of this different flow from what we called site B during treatment that looked very different than an adjacent site we call animal, where we can see that there's flow dynamics happening that can also kind of bring up nutrients to the surface. So it's important that you all are able to recognize the surface accumulations and how they pile up, because that does pose a risk, especially for, say, dogs, as a health risk. But all in all, the whole lake is still catching up, and that balance that we're talking about is still unknown. There's just a lot of other factors that play into it. And so that's what we're trying to convey, is that we probably don't know. And so not just to live with it, but a lot of lakes are going through this where you still have that phosphorus in the lake of a 20 parts per billion. There's still going to be dynamics that allow like this upwelling of nutrients at different times. And there's going to be accumulations at certain parts of the lake where you maybe never see on another side. But it is as different as the wind blows and as different as the sun, might come up. And so there's just kind of a variation day to day that we hope that you guys still recognize. But all in all, it could be worse. And I hate to say that. I've gotten a lot of people that are outside of New Hampshire say that to me, that, wow, do something now before it gets worse. And I think that all the efforts that everyone has put in on all ends have really contributed to decreasing phosphorus. It is just going to probably be a natural part that you continue to see. But at the same time, there are lakes that eventually just don't see that surface accumulation anymore. And it just sometimes takes a little bit of time for those seeds to be removed from the system. And there's a lot of different types. So we're talking about a lot of different food web connections, and I'd be happy to follow up with some resources and literature to help kind of explain that better. But we don't know. We would like to continue monitoring that aspect of it.
Go ahead, Kevin.
This is an extremely tough pill to swallow for the people who live at my end of the lake, who have not been able to go in the water since September 14th. And there are year-round people, and it's been very warm. And I understand that these are shoreline accumulations, but that's where we and our dogs go in the lake. Are we relying on plankton to fix this?
No, I don't.
Go ahead, Amanda.
Go ahead,
Sorry.
Amy. Well, just regarding plankton, no, we're not. Obviously not. I think that there is probably, and I'll let Amy and Dave and others speak to this, but there is probably some addressing of like how do you clean up beaches better? Maybe we can all collaborate on that, where maybe there is a way to clean up these shoreline accumulations safely and effectively. And that's, I think, where we could all brainstorm well on that. But it's not very not very well laid out as a policy and a practice across many states and countries. But yeah, Amy, you speak better to this topic.
Thanks, Amanda. Yeah, we are not at all saying that we are waiting for the plankton to come in and save the day. It's much more complex than that. And what we are saying is that it's too early to have a full appreciation of what the aluminum treatment did and how it will transform Lake K going forward. It is something that you just need to have patience for. And I know that's hard to ask with the degree of blooms that you had, but we are seeing progress and blooms have been reduced and nutrients have been reduced. I just don't think we are quite there yet to achieving better conditions in the lake. And there is a lot to be said about those resting spores that are in the sediments. They do play out, and we've seen a lot of literature and we've had a lot of other people in other states talk about how those do play a factor in nearshore shallow zones. And if you do recall, a lot of those blooms that happened in the past, they did wash up on shore, and those spores are right in that zone where they could pick up nutrients and sunlight and grow and manifest into blooms. So near shore blooms. So yeah, it is just something that you're going to have to work through like we are and just continue to monitor it and see how things are improving.
I do have a question that kind of involves both of these concerns. So most of this is accumulating at the east end of the lake. And a lot of that is driven by the flow of the water and the winds and pushing it and all that kind of thing. But when we do our remediation around the lake and 95% of the phosphorus is external, should we be focusing our boots on the ground efforts and our remediation of individual properties at that end of the lake? Would it make any difference? That's my question.
I think, yeah, that's a great question. I wouldn't necessarily focus on that end of the lake. I would focus on properties that are just generally closest to the lake because they just have a more direct and short, conduit to getting into the lake. But, versus something that's very high up in the headwaters. But certainly every site in the watershed is important. But I would focus on some of the immediate sites around the lake, regardless of, north or south, east or west end of the lakes.
Thank you.
Kevin's got a question.
When we talked about external phosphorus loading, still is a huge problem. But then I forget who was saying it, switched into the what I'll call recycling of the big bad blooms that we had. Is this phosphorus coming from those dead blooms? Is that part of the external phosphorus load that we're talking about?
So we all have to remember that the lake is the low point in the landscape, right? Everything comes into the lake and settles in the lake, and everything that's generated in the lake eventually dies and recycles in the lake. So the lake itself is going to continue to foster that growth. So yeah, it's a combination of external and internal sources of nutrients that are feeding the productivity of the lake.
But
Yeah,
the dead cells are considered internal load or external load, I think is what Kevin's asking.
They'd be
We know they
considered
feed it, we know it
internal load.
recycles, but
Yeah. Yeah, once the phosphorus is in the lake in whatever form it takes, if it's, remineralized from a dead cyanobacteria cell, that would be considered part of the internal load.
okay. If I may, one more question. You were talking about one of the slides, interestingly, showed what cylindro and microcystin, I think, are not toxic. So that leads me to ask, why would we have a watch or an alert in place if it was not toxic? Would we? In that case?
So I wasn't saying that the toxins are not toxic. All three of those are potentially pretty heavy hitting toxins. what I was saying is that we didn't always see toxin production. And because we do not do toxicity testing during the growing season, we use cell counts as a guide for potential toxicity. So historically, we had based our watches and warnings on cell count and preponderance of cell count around the lake. And I kind of jumped ahead on the history slide, but I was going to say that we had a change from 2024 to 2025 where we used to do watches and warnings on lakes when there was just a ribbon of cyanobacteria on shore. From 24 to 25, we started switching that to just color coding points on a map based on algal density and not issuing watches or warnings for most of our lakes. We did this year for Lake Kanasatka because the cell counts at some of the points were fairly high. So we did put a watch on the lake. Now, that's not always the case. You could have, so looking at your data, you could have very, very high cell counts. You had some cell counts that were in the millions a couple of times. And historically, those have not been associated with toxins. However, the inverse of that is true. You could have very low cell count and very high toxin count. So we tend to, with our 70,000 cells per milliliter, be very protective of public health by saying, okay, when we reach that threshold, we're going to put a watch or warning on the water body. But
I see.
Yeah, the big change there is we're not issuing watches or warnings anymore for just ribbons on shore. It's more for the much wider spread blooms across a water body.
And
So
also what I
context has
heard is
changed.
it's difficult to, we don't measure toxicity, a tough word for me to say. We don't measure that, right? We're using just the cell count as average isn't the right word, but a metric of what we do know in terms of relative toxins. 70,000 is the number that has been settled on. But as you point out, Amy, it could be not toxic at 2 million and highly toxic at 2,000. We don't really know.
We don't know. And that's the hazard of saying something is toxic or not. But we just try to be precautious with those cell counts. And we do measure the toxins, both UNH through Amanda and through our own laboratory. Michelle will be doing some toxicity testing this winter. The problem is we don't do it in season. We only do toxicity testing after the season is ended. So in season, we use the cell counts. And then afterwards, we run the analyses and we couple the toxicity presence, absence, or amount of toxin with the cell counts after the fact. So just during the growing season, we have to have a sample and do a cell count.
Thank you.
I think Bree's had her hand up for a while.
I just have a comment, and maybe it's a little bit more positive and less of a question, but I really want to emphasize how important it is for all of LKWA and all of your residents to stay positive about the work that you're doing with Boots on the Ground and the ongoing Sandy Cove projects. Just for examples like the monitoring and communication and responsiveness to everything, like it does make a real difference for the lake and the community as a whole. So even though you're seeing these shoreline blooms appear, and I know and understand how discouraging that can be, it doesn't negate any of the progress that you're making or that you've made in the past. And just, it's taken Kanasatka a really long time to get to the point that it's at. So it's going to take a while to bounce back from that, even with all the efforts that you're making. And I know it's been a years long process. So just want to push to keep staying proactive with everything and constructive, and it's helping other residents understand that these challenges really are part of a broader long-term process, and that your efforts are really central to helping to save the lake. That's all.
Have some faith. Kevin?
Yes, there were sampling methods were mentioned, I think 3 times during this presentation. And all the samples this year have been taken by me and submitted by me. And if I'm doing something wrong, maybe we can talk offline about, how I can do it more efficiently. That's all.
Eileen's got a hand up.
Yes, I don't know if you guys can hear me, if I have bad, a bad mic.
We have
We hear
you
you.
echo, Eileen, but we can hear your question.
Okay, so two things. Can we get some results after that toxicity testing is done? Okay, would you share them with Kevin?
Absolutely. Yeah, we'll share them with the Lake Association as a whole.
Thank you. Second item, so it seemed like, a recommendation was made to do some additional testing this winter. Will UNH be doing that for us?
I would like to say yes. Bob's not here right now. Oh, okay, he is here. Yeah, we would love to help, and that's why we'll hope for good ice coverage, and maybe we can get out there with DES and Laura, perhaps.
Thank you.
Plan that. And Kevin, also I would say, I think the samples, not that I'm with DES anymore, I'm just saying, I think the samples you're collecting and with the photos really helped, actually kind of gave that perspective of like this, the accumulation effect is dangerous. It just is. It could be a ribbon. It could be a dog or a child drinking the wrong bit. The risk is low. But I think that you're capturing the worst case scenario. And that was definitely my approach for several years, just so people could tie that to a photo. But I think it really helped to also show the distribution a bit. And so there's also going to be new guidance from DES on that, but it's, maybe good to get a whole water representative, represent the whole water versus a shoreline accumulation. But I think the photos help, but that's me outside of DES speaking.
Thank you.
Yeah, photos and samples are very helpful because we can't be on every water body every day. So we definitely appreciate that bird's eye view at the lake, and we encourage those samples to keep coming, and we encourage more people to keep an eye out and collect samples as well. That will just inform us better.
Well, you guys have gone 5 minutes past what we requested, so I really appreciate the firsthand information and answering the questions that we've had. I want to thank you very, very much for taking the time out again to explain your findings and explain to us laymen who aren't scientists, because we do see it. We're on the lake, we see it, and it is disheartening, but at the same time, I have faith. I have faith that the work we will continue to do will, bring Lake K back to not quite original, but better. I really feel that in my heart. I think this is a special lake, a special place, and the group of people that are attacking it all have a good special feeling about that lake. So that's the best we can do, I think. If there anybody else have anything to say, otherwise I think we should probably we could close the meeting. We'll get a copy of Amy's PowerPoint, and you said you were getting a transcript too, so we look forward to those. And again, many, many thanks for being our partners and explaining these things to us, because we just don't know, and you guys have a lot more expertise than we do. Okay. Anybody else?
Thank you.
Thank you all.
Appreciate it. Okay.
Thanks
All right.
very much.
And for the Lake K board members on the call, we're going to adjourn this meeting and then